Alright, hello everyone. Welcome back to Computer Science 201. So, let's begin today with any announcements that I have to make. So, what are the announcements? Basically, so the coding portion of Exam 1 is out. Exam 2 is out. The MCQ portion will be out sometime today. Basically, I intended to kind of release this on Friday or maybe Saturday or maybe Sunday. Since I'm releasing it today, and you generally get a week for everything in this class. So what you're going to have is, so it starts on Monday. Well, I don't mean the MCQ. The whole exam starts on Monday. And so it will end the following Monday. So that's next Monday, 4/26. Okay, so the thing about that to realize is, right, it's at the same time as your project. And so, of course, you might have, if you've looked at it already, you might have noticed that instead of 5 questions, there are 4 questions. So that's shorter, right? Theoretically. And one of those questions, I'm not going to say, so the thing is that I think the way to say it, the way to say it is that it's not necessarily going to be, it's not necessarily going to like copy paste directly into your project. As in, if you copy paste it without making any changes, it probably won't work. But basically, the logic that you're going to code can either be reproduced, reproduced, or alternatively, I mean, you can copy paste and then modify slightly. So I'm not going to say it's going to be like a perfect fit, but I tried to make it. So the goal for the fourth problem is that it's still self-contained, right? You don't need the rest of the project to work. You don't need a lot of the other code to be functional, right? You can code this problem without having coded a single line for the rest of the project. And so therefore it's self-contained. So you don't need to start on the project to do this problem, which is one of the goals. But, right, it's also definitely part of the project. So it's part of the project, but your project may be coded slightly differently, and of course it's all up to you, right? The idea here is that the coding of the project is 100% your decision in that sense. So it's kind of up to you how different it is. So basically what I'm saying is like the function signature, the arguments you pass in, you might not need to pass in all those arguments to the same function in your project. You might need to modify that. You might need to change a few things around, but it should be basically what you need for the project. So like 99.9% useful. So that's kind of the idea here. And I know that we have to, unfortunately, we kind of have to have the second midterm overlap with the project. And so this is my attempt at, so there's 3 questions that are not related to the project. There's 1 question that is, and I think that question that is, because I tried this last semester, and as it turns out, most people didn't do very well on that exam question, and the reason why is because it required you to, like, code half of the project to get up to the point where you understood the problem well enough to do it. And so that's my whole argument here, is that I don't think you have to do that here. I think I've kind of fixed the issue. Not that it's the same project, but I think I've fixed that kind of dependency problem where you might have to do so much extra work just to get to the point where you understand the question. I don't think that's true here. So anyway, okay, so that's all I really have in terms of the exam. Maybe I'll talk about the multiple choice questions a little bit, so, that's all. Okay, so that's enough for the exam announcements. So I think now it's time to start talking again about sorting and searching. Of course, we haven't really talked about searching at all. So let's keep talking about sorting. And so, let's recall the two different classes of sorts. And of course, again, we're not in a data structures class here, so I'm not expecting you to be completely conversant with what I mean by all this, but what I do expect is for you to kind of understand the difference. So here's the quadratic sorts, right? And here's the n log n sorts, or alternatively, some people, you can just call them logarithmic, though of course it's not. So this is not 100% true. It's not 100% true that they're logarithmic because they don't run in log time. They run in n log n time. But, you know, you can excuse the shorthand, right? So what are the three quadratic sorts that we talked about? One of the three quadratic sorts was bubble sort, right? And then we did selection sort. And then we did insertion sort. Okay? So what should I say about all these sorts? This one has lots of swaps, right? Basically, what do you think a bubble sort as? And then we'll watch another bubble sort happen. So what does bubble sort do? So bubble sort basically runs through our list, and it checks if each pair is sorted. What do I mean by that? So it checks elements 0 and 1, and if they're out of order, it swaps. Then it checks elements 1 and 2, right? And if they're out of order, it swaps. And then it checks elements 2 and 3, and perhaps swaps 3 and 4, etc. And maybe swaps, etc. until it goes to the list once. So that's one iteration of bubble sort. And then what bubble sort does is it knows that after one scan through the list, so one scan isn't good enough to guarantee sortedness. It's possible that it will scan through once. So if you think about it, if you put a sorted list into bubble sort, it'll scan through the list once, and then remember that bubble sort maintains a Boolean flag variable, right? Which it detects if a swap is done, right? If no swap is done, then the thing is sorted. And what I mean by thing is the list, right? And so if no swap is done, that's our exit condition, right? So what we have to do is we have to keep scanning through the list until we get to until we get to a condition where no swap is being done, and then the list is sorted and we're finished. So that's the idea here, right? So you scan through the list, you swap every pair. If you can stop swapping, then you're done, right? But you have to go through. The moral of the story here is you need to do a full scan at no swaps. So let's do a bubble sort here. Let's pull up the visualization. Here it is. And so let's see here. Let's run the sort. And let's see how fast this thing is going to go. Okay. Let's see. Let's slow it down just a little bit for me. Okay, that might be too slow, but you see here what it's doing, right? It's going through every pair of elements, and it's swapping if it needs to, right? Here it's going to swap. Here it's going to swap. So 47 is pretty big, so it's going to keep swapping until it gets to the end, right? Well, almost. It's going to not swap here, and then the last one it will. So notice that the other thing that bubble sort does is it always carries the maximum element to the end. So for instance, 48 is, well, we're not going to see it here, but it's always going to move these elements. It's going to try to move this one as far as it can. Once it reaches 46, then it'll pick up 46 and start moving it. So we see here that we don't have to swap 40 and 46, right? Because they're in order. But you know that 46 isn't 44 and 46 aren't in the right positions. But bubble sort can only really carry one element backwards. And so here the point is that we're going to end up seeing that 46 is going to get carried backwards because it's going to compare with 4 and it's going to say I need to swap you, and then I need to swap you, and then here it's a bunch of stuff that's in order, so it doesn't do any swaps here. But remember, it's looking for a full iteration where it hasn't done any swaps. So let's increase the speed just a little bit. I think maybe a little bit more. There we go. You see here that it's not carrying elements back very far. That's the problem with bubble sort. So bubble sort only carries this element 2 back a single position, and this 4 back a single position at every time. So that's why this list here is actually going to take a significantly longer amount of time to run through the sort, because you see, if like one of the elements, for instance 2, where it was at the end, it would take a full n swap backs, right? And you know you can only kind of push this back once per scan, and so you can push things forward more than once per scan, right? Because the scan is moving forward, but you can't pull things back because that would mean that you would have to start to like reverse order or something like that. And so here, basically what ended up happening right at the very end, what ended up happening is it saw, okay, let's do a scan. We did 2, 3, 3, 4, 4, 5, 5, 15, 15, 19, and 19 versus 26. And then it said, wait a second, I never had to do any swaps. So at this point we know the list is sorted, so we don't actually have to keep scanning through here. So bubble sort, at least it detects when it's kind of done, and it doesn't do quote unquote extra swaps when it doesn't need to. But yeah, okay. Alright, so now let's talk about selection sort. So selection sort, let's see the way that this thing works. I guess there's a select max sort and there's a select min sort. Let's assume that this is the select min version. So the first thing it's going to do is it's going to scan through the entire list, right? And it's going to look for the minimum. And technically what we're actually looking for is the min index, so it's actually storing the location of 2. And then it does, instead of doing a whole bunch of different swaps, it only does one swap. So it's looking for the thing that it wants to put in position. So 2 is at position 0, 3 is going to go into position 1, then 4 is going to go into position 2. It's just looking and looking and looking. It has to scan through the whole list until it finds this, and then it can swap. Now it's going to look for the next minimum, right? The next minimum is going to be 5, so it's in the correct position. It doesn't have to swap. What's the next one? Here's the next minimum, I think that is. So it's going to swap it back one position. The only problem with selection sort, you see, is that it had the minimum at like this. Here it had the minimum at the first attempt. Here it had the minimum right at the second try, but it just didn't know, right? It didn't know or care that it had the minimum. It had to scan through the entire list again. So that's the issue with selection sort. And basically all of these sorts, and I'll explain why they're quadratic time in a more theoretical way in just a second, but I just want to go through them and just kind of show you how they're working. So remember, I always call selection sort the find min sort, or technically you could use the find max sort and stick it at the end. So the reason why I call it the find min sort is because it finds the minimum in the remaining list, and then it swaps it back to the position. So if you ever have a hard time distinguishing between selection sort and insertion sort, because you might think to yourself, well, selection sort inserts the minimum, and insertion sort selects things as well, so it's a little hard for me to understand, which actually it was for me when I learned all these names. Selection sort and insertion sort the difference between them always confused me, and I think it's partially because the names are not very specific. So here, I call selection sort, it's the find min sort. And the reason why is because that's basically what it does. It finds the minimum and then it swaps. Okay? So let's write that down in our little journal of sorts, right? Here's my little journal, and I'm just going to write down some things about selection sort. I'm going to call it the find min sort, right? Because what it does is the inner loop finds the min in the remaining list, and the outer loop does one swap to put it in the correct position. So the cool thing about selection sort is that it only is going to do up to n. It could do less than n swaps, but it's only going to do up to n swaps in a list of size n, and the reason why is because it's only ever going to swap once it knows it has the minimum. So bubble sort swaps a whole bunch of times, right? It can actually swap basically every time it goes through the loop, and I'll do a little bit of math to prove this, but every time it goes through the loop, it's basically going to do something like n squared minus, or it's going to do n minus k swaps for k equals the number of times we went through the loop, right? This is like the worst case for bubble sort, is that it's going to do n minus k swaps for k is equal to the number of times that we went through the loop, and for n is equal to the number of elements in our list, right? N is equal to the number of elements in our list, right? And so then the thing is that here we have to sum n over k for k equals 0 to, say, n minus 1, or maybe up to n. It doesn't really matter because at that point you're just summing an extra 0 on. And I'll show you exactly how that works. It's going to end up being something approximately n squared divided by 2. All right, so that's the maximum number of swaps that you can do here. For the selection sort, you're only going to do up to n swaps, but the find min step, right? It doesn't matter that there's n swaps. The number of steps, the total number of steps in a selection sort is also n squared over 2. So unfortunately, and I'm actually not, I think there are conditions under which doing a lot of swaps is more inefficient than finding the minimum index, and there's a lot of conditions under which doing a bubble sort might actually be better than a selection sort. So selection and bubble sort kind of compete with each other. I think there's some cases where running all these extra swaps is worse, and then there's some cases where doing basically having to be the problem with the selection sort. So here's the basic problem with the selection sort. So the problem with the selection sort is it always runs exactly the same way. So if you have a sorted list, bubble sort is going to scan through the list once, detect that it's sorted, and stop. So bubble sort can actually run much faster than its worst case, but selection sort can't do that. Selection sort is always going to run exactly the same way, regardless of the shape of the list. If the list is sorted, if the list is completely unsorted, if it's completely randomized, if it's reverse, it's always going to do the exact same number of steps, because it can't, the way that it's built, it can't do any different. It's like, the ultimate determinist, right? It just doesn't, it can't really decide to do differently, right? Can't make any decisions to make this process better. I'm sure that there are improvements to selection sort, but generally when we teach these sorts, we teach kind of the standard version of the sorts with no significant improvements, and the reason why we do that is because if we taught all the complex additional improvements, then then we could kind of keep competing against each other until we invented a new sort or something like that. So it's like the merger of all three. So now let's talk about insertion sort. Insertion sort is kind of like an improved bubble sort in a way. So, and I usually call it, so it's not the find min sort. I call it the pull back sort. And you might, when you see the visualization, you'll understand why I call it the pull back sort. And so let's look at the visualization, right? So if we look at the visualization, we click on Insertion Sort. And I know that I've gone all over all of this last class, but the point is that, like, the right answer is always just keep saying the same stuff until people believe you. So, random. Let's get me some random lists. Random. That looks good. I don't know why I'm... Okay, that looks good enough. So let's do this one. I don't know what looking good enough means. So what I mean by a pullback sort is that you're going to start at the second element here. And you're going to ask, how far do I have to pull it back until it's in the correct position? Now, it being in the correct position is only a temporary thing, because what we're going to do is we're going to sort this little list here. So the first step is we're going to swap 30 with 33. And then that's all we do in the first step. So we swap 30 and 33, and then we go into the second loop. Right, so we're going to pull this back, pull 30 back, and stick it in at the front. Okay. Now we're going to look at 45. We look at 45, it's in the right position because it's not less than 33. We look at 40. 40 needs to be pulled back by 1. There we go. And basically, how do you know when to stop? Right? You know when to stop when the element, say 40, is bigger than the element previous. So 40 was smaller than 45, so it needed to be pulled back by 1 step, but it's bigger than 33, so it doesn't need to be pulled back by more than 1 step. So here we go. Let's pull, and this one's got to be pulled back all the way, right? 9 is less than all of this stuff. So pull it back all the way, stick it in here. Pull back, right? Pull back, and stick it in. And so then the same thing here. We'll have to pull this all the way back, not until 9, but just right before 9. And that's what we'll do here. Let me increase the speed a little bit because that might get annoying. The next step is 48, which doesn't have to be pulled back at all. 38 only has to be pulled back with 3 elements. The cool thing about 50 is that it doesn't have to be pulled back. 43 has to be pulled back, 3 elements. 47 needs to go back 2. 43 needs to go back, I guess, 3 or so. Maybe, 4, I guess. Yep, 4 elements. So, yep, there we are. And so we see why this is I call this the pullback sort. It picks up an element at position K, and it pulls it back until, you see, it's going to pull this one back until it sees this 18 here, and then it'll say, okay, I'm done. Because I know that at this point, I don't need to pull the element back any further. Here, I've got to pull you all the way back. So you see that it's kind of the opposite of bubble sort, if you know what I mean. So bubble sort does the sorting going upwards. Insertion sort does the swapping coming backwards. And is it better? And the answer is empirically yes. So insertion sort generally outperforms bubble sort. It definitely outperforms selection sort. So of all the quadratic sorts, generally insertion sort is considered to be the best of the 3. The reason why we teach all 3 is because generally, if you're going to actually sort stuff, you never use basically you just use insertion sort if you're like required to do a quadratic sort. But in general, you're going to say, I'm not even going to do any quadratic sorts. The only reason why we teach quadratic sorts is because they're definitely simpler than the logarithmic sorts. They do things that kind of make sense to you. They do a bunch of swapping of elements that, direct swapping of elements. They're not quite as abstract as the next type of sort that we're going to talk about, which is the quicksort, and then we'll talk about merge sort again. Well, not again. So we'll talk about quicksort again, and then we'll teach merge sort. So cool. Now this thing is completed. So what happens? Let's create an increasing sorted list. Let's try again. Make it longer. What happens if we sort this with insertion sort? So what's going to happen is notice it's going to look at the second element. It's going to ask, do I need to pull it back? The answer is no, I don't. So, cool. Do I have to pull this back? No, I don't. How about this one? No, I don't. And you're going to answer no, I don't for every one, because you see, if the list is sorted, it's already in a position, every element is already in a position where it's bigger than its neighbor right beneath it, or right behind it, or whatever you want to call this. And so if that's the case, then you see that it's going to ask, do I need to swap? No. Do I need to swap? No. So actually, this is doing just as good as bubble sort. So watch this do just as good as bubble sort, because here what it's going to do is it's going to reach the end of this list, and then guess what? It's sorted. It can stop. So this is one of the reasons why insertion sort is actually favored, because it performs better in cases where the list is nearly sorted. It performs about the same as bubble sort in just completely randomized lists, but it's going to perform a lot better if the list has sorted chunks in it. As it turns out, when you're actually doing a lot of coding, it's common that you're going to run into lists with like sorted chunks in them. And so that's why you prefer insertion sort. So remember we implemented like a little racing function for sorts. So let's race the two sorts. Let's say who's the best, right? So let's do a time test on bubble sort, and let's do a time test on selection sort, and let's do a time test on insertion sort. And now I have to modify this a little bit, because if we do, I promise you that if we do these last two tests, we will never finish. I'm not even 100% sure about this one. I think this one will finish, but it takes a while. So anyway, let's do this. Okay, so let's print out bubble, selection, and insertion, and then let's erase them. And so let's see which ones perform fastest. So we're not going to do anything on 100,000 elements. We're not going to do anything on 1,000,000 elements. The reason, and you'll see the reason in just a second. So here's bubble. So remember the point about being a quadratic sort, right? This one takes on order of 0.00051, 0.001. So if this looks like a real good condition for the bubble sort, and it took about what? So I guess 0.000. So this is about 1 millisecond. So it took a half a millisecond here. It took about a millisecond here. About a millisecond here. And then here it did about 155 times worse, about 150 times worse, 150 times worse. So you notice that 150 is about 100. I mean, I know it's not, but it's about 100. And so you notice that here, increasing the size of the list by 10 increases the time that it takes to run by technically about 150, but really about a factor of 100. And then here you notice, same thing. So bubble sort took 15 seconds. So here it took 0.15 seconds. When we go up from 1,000 to 10,000, we multiply by 100. So it's going to take us 15 seconds, 16 seconds, 15 seconds. And so selection sort, you see, selection sort, it says it takes 0 time, right? But of course you're going to tell me it's not really taking 0 time. What is it actually doing? It's just taking less time than the time function can detect. So even though it looks like we have all this extra precision in our time function, like, you know, it looks like we're getting times down to all here, probably the answer is that we are definitely not, right? It looks like our accuracies are actually around 1 millisecond, and here, these are probably about, you know, these are like maybe 100 times faster than that, so if they're down here, it just looks like 0 to the computer. And so here, we see that it isn't quite 100 until we get from 1,000 to 10,000. So from 1,000, it's about 38. Let's just estimate. I'm going to call it 38. And then here selection sort did about 3.8 for 10,000. So 1,000 was 0.0393938, whatever, something in there. And so you see selection sort did a lot better, right? And the reason why selection is doing a lot better is because all of those swaps that Bubble had to do, it costs it, right? It costs Bubble sort in swaps. So it's better to do a bunch of extra comparisons, right? This is making us do a whole bunch of extra comparisons. But the advantage is we're not doing as many swaps. So you see that swaps are more expensive by about a factor of 5 than a comparison. I think that's a pretty cool thing to see, right? So doing the swap is about 5 times as expensive as doing the comparison. Nice. All right. And that's only in our implementation. I think the one reason is because we did an extra function for it. If we probably didn't do an extra function for it, we would see different results. Probably a slight improvement for bubble sort. But then you see here's insertion sort, right? Insertion sort performs better. Actually performs worse here. Look at that. It's doing worse. Oh no, okay, it's doing slightly better, I guess. No. I stand by my original thing. It's actually doing slightly worse than selection sort, which is funny because it's kind of the industry standard. You don't generally use selection sort for almost anything, and you use insertion sort. But again, you see the most important point here is that this size 100 list took about 0.001 second. This one took, and I'm just rounding them up because they're all 0.9s, or 0.09s. You know, I'm saying that this took about 0.1, and so that's 100 times as bad. And then this one took about 9 seconds, about 9 seconds, about 10 seconds. So, you know, every time you increase the list size by a factor of 10, you increase the runtime by a factor of 100. And so you see now why I refused to run this thing on a list of size 100,000, because the guess is if I increase this, right, if I increase this to a size 100,000, it's going to take probably something on the order of 1,000 seconds. And you might ask, well, what is 1,000 seconds? So I divide 1,000 by 60. On average, it's going to take 16 minutes, right? 16 2/3 minutes to finish an insertion sort on a list of size 10, 100,000. And if we tried to do it on 1,000,000, it would take, let's see here, it would take 27 hours to finish on a list of size 1,000,000. And so you see that it's getting ridiculous, right? You don't want to waste 27 hours for a list sort operation, even if it's on 1,000,000 elements. You just don't want to wait that long. So that's why we are not doing it, right? Okay, cool. So that is the sort races between bubble, selection, and insertion, right? And so you see kind of, and I promised you that selection was worse than insertion sort, but I guess it wasn't. I guess it did okay. Let's run it again, and in the meantime, let's let it run in the background. And in the meantime, I want to talk about a new sort. So I didn't talk about Quicksort again, and I won't talk about Quicksort. We'll do that as a review after I'm done talking about my new favorite sort. So basically, what we're going to do here, there's 2 logarithmic sorts that we're going to talk about, and then one that we're not going to talk about. So there's Quicksort, and that was last time. We implemented Quicksort last time. Remember, that involves the bigger list, equal list, lesser list, right? Bigger, equal, lesser lists, and you stick them into each list based on the pivot. I know I'm reviewing it. I said I wasn't going to do it, but I'm doing it anyway. And then remember that the pivot is just a fancy name, currently for our list at element 0, right? And so if it's bigger than the pivot, it goes into the bigger list. If it's equal to the pivot, it goes into the equal list. If it's lesser than the pivot, it goes into the lesser list. And then the last part of, and the absolute moral of this story, right, is what do you do? So after you have successfully sorted things into the list, then what you do is you do a quicksort, on the lesser list plus the equal list, right? Because the equal list is already sorted, it's all I equal. And then you quicksort the greater list, and then you return that. And that's how quicksort works, right? So quicksort sticks everything into a list based on its pivot value, and then what it does, and I guess I should really flip these two lines. Quicksort is recursion. Yes, it is. Quicksort is very much recursion. Basically, all the logarithmic sorts require recursion of some sort. And so, okay, and that's really it, right? You stick things into their lists, and then you recursively sort. And remember what the edge case is. Remember, and I'm doing this kind of backwards-ish, but the edge case is that the pivot, you just take the first element of the list. Now, it's better if you don't do this. There's ways to improve upon it, blah, 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 but that's the absolute simplest. In fact, it's even better. So a better way to do it, I know it sounds stupid, a better way to do it is actually just to randomly pick the pivot. To basically do something like pivot equals the list, and then you do a random.randint 0 to length of the list. This is actually better, significantly better, on average. This is a anyway, okay, but I don't want to talk about quicksort right now because we did quicksort last time. But we want to talk about merge sort. But okay, so the first thing I want to do is not talk about merge sort. And you say, wait a second, that's a deception. You said I want to talk about merge sort. I just want to talk about a function called merge, okay? And so merge is not merge sort. Merge is a part of merge sort. And so what merge does is it takes two sorted lists and it makes a bigger sorted list. Okay, and that's all it does. All right. So you might think to yourself, well, how do I get the original two sorted lists, right? If I'm going to end up doing a merge algorithm and I'm going to call it a sort and blah, blah, blah. Don't worry about any of that right now. What you want to assume, right, is that merge is a function that takes two parameters. Merge takes first list and second list. It is similar in theory to quicksort. It operates kind of differently, but again, so the point is merge takes two lists, and our assumption is that both of those lists have to be sorted, and then it's going to output a bigger combination sorted list. That's what it's going to do. Okay, so how is it going to do that? So let's write a merge algorithm, because we've done a bunch of non-coding right now, but let's do some actual coding for once. Where am I? Here am I. I guess selection sort's beating it. I think it might be because of how we're doing this this swap function, the fact that it has to call an extra swap function. But let's ignore all of that for now and just pretend that everything is happy and everything is great, right? Don't worry, be happy. So, right? So the point is merge is going to take first list, second list, and it's going to output a sorted combination of the two lists. And so first list and second list must be sorted already. So you might, again, this might be breaking your brain initially, so you just have to kind of go with it. Don't think about it too hard, right? Just be like, okay, if I'm given two sorted lists, how do I stick them together? Well, the answer is you do it like this. Right? What you do is you have, let's say that you have two sorted lists like this. Let me make some blocks. And let's assume that they're of the same size. They don't have to be of the same size, but you know what, let's assume that they're not of the same size. So let's take two differently sized lists. It really doesn't matter. In our algorithm, they actually will be the same size, but whatever. So let's make this 2, 5, 7, 13, 19, 21, 35, I guess, because my hand was on the 3, 37, 42, and 49. That's a sorted list. And then what we're going to do is the same thing here. So we're going to start at, say, 7, and then we're going to go 12, 18, right? 31, 77, 92, 108, and 112, right? And you might be asking yourself, like, okay, I don't get it. What's happening? And the answer is don't worry about it, right? We're almost there. So, all right, let me just space these out. Oh, I said that. Dude. Okay, for anyone who has a little bit of OCD, or for anyone who's just bothered by the fact that they're not straight like that. Okay, so how do you merge? What you do is you say, okay, I'm going to take the 2, I'm going to stick that at the front, and then you look at 5 and 7, right? 5 is the smallest, so you stick that one in. Then you look at 7 and 7. It really actually doesn't matter, so we'll take one of the 7s at random, and then we'll take the other 7, right? But then where are we? So we're at 13 and 12, so we're going to compare 12 and 13. Take 12. Right? Then we're going to take 13. Well, I should say, then we're going to compare 13 and 18. Take 13. Then we're going to compare 18 and 19. Take 18. Then we're going to compare 19 and 31. Take 19. 31 and 21. Take 21, right? 21 is the smaller one. 35 and 31, right? Take 31. So basically, what you notice is that I have a secret pointer. The pointer is pointing here, and the pointer is pointing here. So once I take 31, then I move the pointer to the next location. And I don't mean a pointer as in like a C++ pointer, if you know what I'm talking about. I just mean an index, right? I'm just maintaining index 1 and index 2. So I compare this one and I say 35 versus 77, take 35. 77 versus 37, take 37. 77 versus 42, take 42. 77 versus 49, take 49, right? And at this point, then we're out of that list. And this is a good condition because I want to talk about this condition. So now you see our index is pointing to 77, and our index is also pointing outside of the list. So basically what that means is that what we need to do is we need to take the rest of the stuff in this list and kind of blurp it onto the end like this, and we're done, right? And that you do this by saying take 77, take 92, take 108, take 112. And so this is how you would merge things. So let's try to write this into code. So the point here is that we need 2 indices, right? So let's call it first index equals 0, second index equals 0. And then, I've written this function a million times, so I know that this time I'm going to use a while loop. You might think, well, maybe I'll use a for loop. You could do that, but I'm going to use a while loop because it's slightly better. So I'm going to say while the first index is less than the length of the first list, and while the second index is less than the length of the second list. To which you say, okay, I believe you. Now what? Now you say, if first list at the first index is smaller than or say equal to the second list at the second index, then what do we do? So what this is saying is that the first list at the first index is less than the second list where we are at the second index. So what that means is take the thing from the first list. So if the first list at the current index is smaller, take that one. So let's make a result list equals nothing, or empty list. So we say result.pen first list at first index. And then what we need to do is we don't want to take that element again, right? Don't want to take an element twice. So what we do is we say first index plus equals 1. So we accelerate. We don't accelerate. We index the thing by 1. Cool. Else, we do the opposite. So if it's not this, then it's the other way, right? Second index, second list. Just make sure that you never take The one rule is never take from the second list with the first index or the first list with the second index, because look at how they're working. The first index is only constrained by the length of the first list. The second index is constrained by the length of the second list. And at this point you might say, are we done? And the answer is not quite yet. Right? We still have a little bit of work to do. And the reason why we have... it is actually very similar to weave. It is weave. So this is weave, I guess. Yes. So, yeah, I didn't mean to say pointers. I shouldn't... the thing is, you say words and then you realize that they can have double meanings. So here, what we have to do is we're not quite done yet. Right? What we need to do is we need to say, and this is what I'm going to do. It's a little bit of a cheat, but whatever. I'm going to say for index in the range from first index to the length of the first list. And now keep in mind that this index is going to only execute this loop when what? When the first list, first index, not first list. There we go. So when the first index is less than the length of the first list. If it isn't, if we're doing the range from say 5 to 5, then remember that it starts at 5 and it goes up to but not including 5, so it won't execute this loop at all. So that's actually exactly what we want. If we've taken everything from the first list, we don't actually want to do it anymore. So let's do result.append. Let's see, first list at index. And then we do the same exact thing for index in range second index to the length of the second list. And we do the exact same thing, except here we do second list at index. And then of course we return the result. Now, you might be asking yourself, does this handle it? And it does, because only ever one of these, or only one will ever go, right? Either the loop above or the loop below. Technically, one of these has to run for at least one step, even if they have the same number of elements, because at one point, one of the indices will reach the end first, and the other one will be basically one behind it, and then one of them will execute. They will execute at least one step if they're if the lists are just kind of like take from A, take from B, take from A, take from B, take from A, take from B. So you might be asking, okay, so this is making a sorted list, and I always like the fact that I always say sorted list, so it's always a little hard to tell whether I'm saying sorted, like an awful, grotesque list, or sorted, as in order. The answer is, I don't know. I always hear myself saying sorted, like a sorted list, a terrible list of grotesque proportions and, just awful in nature. Okay, anyway, so, cool. So this is our little weave function, our little merge function. So now what I want to do is I want to make a sorting algorithm with this thing, right? So I want to make a sorting algorithm with this. So how am I going to make, so let's just type in merge sort, right? And here's the list, right, that we're going to sort. And so how do I get two lists out of a single list? And don't think too hard, right? How do I get two lists out of one list, right? Yeah, sorted 341 functions. So yeah, the question is, how do I split, hint, split, a list, right? What do? I'm going to split the list. How am I going to split it, right? What's the dumbest possible thing you can do, right? Just take half of each, right? Maybe? I mean, let's try it. Like, the dumbest possible idea is just split the list in half from, say, 0 up to halfway, and then from halfway up to the rest, right? And you might think to yourself, well, good God, that's pretty dumb. Like, is that gonna work? And the answer is, what you do is you will merge sort the first half of the list. So you're going to merge sort the list of, and I'm actually going to use slices here because I'm extraordinarily lazy. The list divided by 2, like this. And then I'm going to merge sort the list from the halfway point up to the length of the list, like this. So we'll merge sort these two, and you might say, wait a second, how are you merge sorting? Right, you don't, so let's call this the first half, and then we'll call this the second half, and you know where this is going, right? Now you might say, okay, I have a first half, and once it comes out of merge sort, there's one thing we know. We don't know anything about what merge sort is doing at the lower levels. And of course, it's yelling at me, merge sort doesn't return anything. Give me a break. I'm about to. Hang on, PyCharm. So the first half doesn't return, the first half is going to be sorted because it's coming out of a sort function. Okay? That's all you know, is that the first half is sorted. The second half is sorted because it's coming out of a sort function. So then what we do is we return the merge of the first half and the second half. Whoa. Now you might say, wait, we cannot just run this thing. Whoa, stop. Right? So why can't we run this thing as is? This is the idea, right? So I'm not saying that this is wrong, it's incomplete. And the reason why is because programming is about attention to detail, right? It's about getting all the little nitpicky things right. And what are the little nitpicky things that can happen? Well, what happens if we try to divide an empty list? Well, so the empty list is also going to give us 2 more empty lists. So the point is that once we get down to an empty list, it's going to keep dividing infinitely. So we don't want that. So what if the length of the list, right, is less than or equal to, say, 1? Well, if the list length is less than or equal to 1, remember that we did the same thing for Quicksort. We can just return the list, because a list of length 1 is sorted, a list of length yeah, exactly, a base case. We want to prevent ourselves from just blasting into infinite recursion and just going down into the depths until Python says, recursion error, depth exceeded, right? We don't want that to happen. So here what we're going to do is we're going to say if the length of the list is less than or equal to 1, then just return the list because, right, any list that's empty, empty list is sorted. Whoops, where am I? Here, right. Empty list is sorted, and also list with X, right? I don't know what X is, but I don't care because this is sorted because, X is in the order that it is, right? Who cares? There's nothing less than it. There's nothing bigger than it. I don't care if it's 1,000,000. I don't care if it's -10. A list of a single element is sorted. All right. So then we have first half is equal to merge sort on the first half. Second half is merge sort on the second half. And that's it. So the first thing we're going to do, how deep is the list? That's a good question. That's a good question. It's a question I'm not going to answer. So actually, I think this is probably my shortest. I normally do a lot more garbage code. Technically, you could even do you could do this all, except for this one, right? You could do this all in one line. You could really make a go of this thing. So, because you could just kind of copy this into here and copy this into here. It'd be just one return line, except for this edge case. And then you could even kind of put everything into one line if you were really careful. But we'll not do that because that's pretty awful. Okay. So, how does merge sort work? What it does is it divides the list in 2, divides the list in 2, divides the list in 2. Now, let's just look at what it's going to do, for example, on a list that's, say, 5, 3, right? So if this is our list, what it's going to do is it's going to divide the list in half, right? This is a list of size 2. It's going to divide it in half, and it's going to get the list of 5 and the list 3. And then what it's going to do is it's going to run merge on that, right? And then merge is going to take these 2 lists of single elements, and it's going to spit out 3, 5, right? So what happens if we run merge sort on, say, 2, 8, 1, 4, right? what it's going to do is it's going to divide it in half. So it's going to say 2 and 8, 1 and 4, like this. And then each one of these is going to get divided in half. So 2, 8. And now you might say, but Eric, it's already sorted. We don't have to do this division. Look at merge sort. Do you think it cares? It does not care. It doesn't notice, right? It doesn't check. So what merge is going to do, so now what it's going to do on the way back up is merge. Well, that's a good question. We'll deal with that in just a second. We'll merge these two, and we'll also merge these two. So we're going to get 2 and 8 back, 1 and 4 back, and then we're going to hit this with a merge. And then what do we do? Now we say it's going to be equal to 1, 2, 4, 8, right? Because you know that a merge is going to take an unsorted or 2 sorted lists to make a sorted list. Okay, so you were asking what happens if we do something that doesn't divide evenly. So let's take a list that has an odd number of elements in it. So let's say 5, 3, 1, 9, 2, something like that. And so the point is that when we divide this list, quote unquote, in half, there's a decision to make. Do we stick the 1 into the list going up into the second half, or do we keep it down in the list going into the first half? And the answer is the length is 5. We divide by 2 with an integer division, so that's 2. And so the slice from 0 to 2 is going to go take elements 0 and 1, and then 2 to 5 is going to take elements 2, 3, 4. So the point is that hopefully, okay. Yep, so the point is that it's always going to kind of stick the odd element in the higher list. And so that's how it's going to divide it. So here we're going to get 5, 3, and we're going to get 1, 9, 2. And then 5 and 3 divided into 5, 3 again. Actually, this is the same as the original example. And then here we get 1, and then here we're going to get 9, 2. Uh-oh. Come on. Hopefully the video is still streaming properly. It seems like it's having some issues. Okay, hopefully it's not having too many issues. I'm going to keep going, pretending everything is fine. So then the final step is that it's going to divide this into 9 and 2 like this. And then I'm going to put parentheses around like this, and then put a bar here. Yeah, sorry about that. Come on, come on. Don't screw me up now. This is merge sort. This is the best part. Okay. Alright, so here it's going to remerge to 3 and 5. And here it's going to remerge to 1, which doesn't merge yet, and then 2 and 9. And then it's going to do this. Then it's going to remerge, not on 3, 5 yet. It's going to merge here, so it's going to give us 1, 2, 9. And then finally it's going to merge the last two things. So it's going to take 1, 2, 3, 5, and 9, like this. And then we're done. All right, so basically the error that it commits, it only ever splits with an error of 1. Merge sort is kind of like the sort equivalent of binary search. That's right. That's true. I mean, it's been postulated that I could be a robot. So, okay. So now let's do a sort test. And remember what the sort test is. We're going to do 10 tests of size 10,000 on merge sort. And the reason why I'm doing this is just to test to make sure merge sort is actually working correctly. Because if it's not, I don't want to commit any terrible sins. There we go. So the list is sorted. There we go. Cool. So I just wanted to do that because I didn't want to see any problems. Okay, so now let's do a time test. Let's time test selection sort. Let's time test quicksort. And let's time test merge sort and just compete. Oh, that's true, I do. Let's print out selection. Let's print out, say, quick, just so that we know which one's which. And now let's print out merge. Okay. So basically we're done with merge sort. Let's run it and see what happens. What are we doing? Here's selection sort. Of course, selection sort. I don't know why it's performing so much better. I think it might be the implementation. I'm really suspecting it's the implementation. And then you see, which is something that you should definitely love, right? It took 3.7 seconds to do this, 3.7 seconds to do this, 3.97 seconds to do this. So it was taking around 4 seconds, maybe. Let's just round up to say 4 seconds for each one. It took 12 seconds to get through all this, and then you didn't even. I mean, I couldn't. Maybe you could. I really couldn't perceive the quick and the merge sort finish, right? Quick and merge sort finish so quickly that we didn't really even get to see them, right? They just kind of showed up on the screen and they were done. So we see here that when we're looking at the competition between the quadratic sorts, even our best quadratic sort here, which is selection sort for some odd reason, but even our best quadratic sort just absolutely gets annihilated by quicksort and even by merge sort, right? They get annihilated by both of the sorts. And there's a reason for that. And the reason is that these sorts run what's called asymptotically faster. And what I mean by that is that as you increase the number of elements in the list, these only increase with a factor of about n, whereas the quadratic sorts increase with a factor of n squared. And you might yell at me because it's actually n log n divided by n log n, a ratio of that, which is going to be something, mostly because of the recursion, yeah, actually. The recursion partially does, the recursion does it for us. There are cases in which quicksort and merge sort behave the same, but you see that quicksort kind of does much better than merge sort on average. The only reason why merge sort exists, and the only reason why merge sort is kind of a dependable sort that gets used for a lot of applications, is that quicksort has some bad possibilities, okay? Quicksort can do really bad, and it can do really bad on sorted lists. It actually performs like quadratically on sorted lists. So it's really bad on sorted lists. Whereas merge sort performs the same regardless. Because if you look at merge sort, did merge sort ever actually care here about anything inside of the list? Did it pick a pivot? Did it make any decisions here? Like merge does, but merge always runs in the same time. Unfortunately it can do really badly. Unfortunately, it doesn't do it. It doesn't, when it's doing badly, it doesn't do it quickly. So quicksort can perform very badly and very slowly. Anyway, but the point is, like, did this make any decisions based on the actual values in the list? No. It never cared even 1 second what was inside the list. It just said, randomly divide it in half starting at the middle point, and merge sort the halves. That's all it said. So it never cared about the structure. So this one, the good news is that merge sort will always give you basically the same time performance, right? Right? Merge sort will always give you the same time performance, whereas quicksort will sometimes give you very bad time performance. Anyway, so that's that. So let's see here. So merge sort is normally slower than quicksort, but not by a lot. And a basic quicksort is usually is prone to some really, really, really bad events. And let me show you what Quicksort is going to do on a sorted list. So here's what Quicksort does on a sorted list, which is why merge sort is a lot better. Watch this. So what does Quicksort do? Quicksort picks the first element as the pivot, and then it sticks everything into a less list, an equal list, and a greater list. So what it's going to do is it's going to stick 2 into the equal list, right? 2 goes into the equal list, and everything else goes into the greater list, right? All right, now what's the next step? The next step is it does the same thing only here, whereas here what it's going to do is it's going to split 5, which is the new pivot. 5 is the new pivot, so it's going to split that into the equal list. And then it's going to put everything else in the greater list, like that. There is no less list, so it's all equal, greater, equal, greater. So this is equal, and this is greater, equal, and greater. And so you see that here, and then the next time it's going to go through, it's going to do the same exact thing. It's going to say greater list, equal list, etc. And it's going to keep doing this until it gets all the way down to a single element. So I'm going to put a bunch of dots, right? All the way until you get down to 112. So the point is that Quicksort here does really badly. And you might think to yourself, like, wow, that's very strange. And so here's the problem with Quicksort, if you do it in the very basic way, is that a lot of times, remember what I said, a lot of times what ends up happening is you get lists that aren't always perfectly sorted, but they're close to sorted, and unfortunately, a close to sorted list also does this, right? Close to sorted lists do this, perfectly sorted lists do this. Wouldn't 7 go into the equal list? It would, in fact. You're right, I didn't care. There we go. But, so, this is actually a slightly better version of the worst performance, but it's still pretty bad. So, we skipped one step here. But, the point is that I want to go over a specific summation. I want to talk about, and you'll see why I want to talk about this in just a second. So let's do some math. So I want to talk about the sum from, let's say, k is equal to 0 up to n of k. All right, and so what does that equal to? That's equal to 1 plus 2 plus 3 plus some dots, plus, say, k, plus some more dots, plus maybe n minus 1, plus n. So this is all the symbology of it. So let's look at the symbology, and then we'll look at the almost. Let's hope this works. So this is probably, I would say, one of the most important sums in computer science. The sum of k's, from k goes from 0 or 1. I guess I didn't add the 0 in there, naughty me. But let's do some examples. So if we just do, say, 1 plus 2, that's equal to 3. Actually, okay, 1 is equal to 1. 1 plus 2 is equal to 3. 1 plus 2 plus 3 is equal to 6. 1 plus 2 plus 3 plus 4 is equal to 10. I'm just doing these as an example. Plus 5 is equal to 15. Plus 5 plus 6 is equal to 21. Whoops, didn't put the 5 in there. Come on, go in 5. There we go. Plus 7, I guess that's 28. And you kind of get the picture, right? So the reason why we need this summation is because this is the number of steps that we're going to do in a selection sort. It's the number of steps in the worst case of a bubble sort. It's the number of steps in the worst case of a quicksort. So it's the worst case of bubble. It's the number of steps in a selection. It's the worst case of quicksort. It's the worst case of insertion sort. Merge sort will never do this. Merge sort will never do this. But if you're wondering how we get quadratic time, this is how we get quadratic time. We say, what's the number of steps? Well, this number of steps is equal to, and really it's reversed. It's like 7 steps plus 6 steps plus 5 steps plus 4 steps all the way down to 1. So there's a cool way to sum this up that doesn't use too much induction. So there's a proof using induction that I'm not going to do because this is not Math 2 or CMSC 203. This is not, there's a lot of things that this is not. So we're going to do this proof that I like, that you don't usually get to see in computer science. But it's a good proof because it makes you think in a different sort of way. So this is how we're going to add these together. I want to make these kind of symmetric looking. Oh, nice. Look at how nice and symmetric looking those are. So, what have I done? So the point here is, we're adding up the numbers from 1 to 7, and then you notice something, right? You notice if you add up 1 plus 7, you get 8. If you add up 2 plus 6, you get 8. If you add up 3 plus 5, you get 8. And then there's this extra 4 left over. Let me just bold that 4 because it's extra. But look at what's happening, right? Look at what's happening. We have 3 times 8 plus 4. Which you might say like, eh? Okay. So let's do it again. So if we choose to pair on here, what we're going to see is that instead of getting 8s, we're going to pair 1 to 6, so we're going to get 7. So let's look at this one separately. So here, we're going to pair 1 and 6 is equal to 7. We're going to pair 2 and 5 is equal to 7. And we're going to pair 3 and 4 is equal to 7. Right? And so basically, this is equal to what? It's equal to 3 times 7. And so let's postulate. So note that we're adding up to 7 here, and this is 8. We're adding up to 6 here, and this is 7. So I'm going to postulate this 7 is really n plus 1. Okay? 7 is n plus 1. And then what is this 3, right? If we notice, there's also a 3 in this next case where we're adding up, what, 1, 2, 3, 4, 5, 6, 7. So 7 divided by 2 is equal to 3 in the integer sense with this extra thing here. 6 divided by 2 is equal to 3. What if we add up these, right? If we add up this one, right, we'll say, oh, this gets us 1 plus 5 is equal to 6. Ah, that is n plus 1. 2 plus 4 is equal to 6. And then 3 is equal to 6 over 2. Okay? So what we're going to do here is we're going to add all this up. And so we're going to end up with here, when we add all this up, is we're going to end up with 6 plus 6 plus 6 over 2. And here we'll end up with, 7 plus 7 plus 7, right? Here we end up with 7 plus 7 plus 7 plus, technically rounded up, 7 over 2 or 8 over 2 or something like that. Oh, I'm sorry, no, we get 8 plus 8 plus 8 plus 8 over 2. So what we're actually getting here is we're getting the number of elements, right? So 3 is really the number of elements divided by 2, without rounding down. So as it turns out, the sum of all of this is always equal to n divided by 2 times n plus 1. And a lot of times you'll see it written like this, n times n plus 1 divided by 2. So what is this number? What have we just calculated here? And so the answer is, in general, all we've done is we've added up 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus all the way up to n. That's all we've done mathematically. But as computer scientists, what we've done is added up the number of steps when we have a for loop, when we have for I in range n, And then what we do is, if we have for j in range, say I up to n. Or alternatively, it's the same number as if we do something like this, where we start at 0 and go up to I. Yeah, unfortunate, isn't it? My internet was fighting me yesterday, so I think... So this is the way to think about it. Whenever you get something like this, and we'll talk about asymptotic complexity next time. So this is a good transition into asymptotic complexity, and we'll analyze the asymptotic complexity of maybe Quicksort or bubble sort or merge sort or something like that, just to kind of analyze it and think about its runtime. So the good news is that computer scientists are kind of lazy when it comes to all of this stuff. So mathematicians would care about all of these divided by 2s and all this extra n plus 1s. If you've ever seen it, computer scientists usually just call all of this stuff, we call it order n squared. So order n squared, that's what we call it. And the reason why we call it that is because the biggest thing in that equation is the n squared part, right? And all the other parts are kind of tiny and not really important. Okay? So the reason why they're not really important is because other factors generally influence the n squared part. So like the hardware of the computer, the various speeds, all that kind of stuff, they influence the computer and the amount of time something is actually going to take. So a lot of the times, the most accurate calculation we can do, the actually most accurate time estimate we can do, if you don't have more information about the exact computer it's running on, right, or anything else, is basically you just say it increases its runtime in proportion to n squared. So what that means is, as we've done before, if something is O of n squared, then it takes, it takes some constant times n squared time, right? So that means time of n is equal to some constant plus lower order crap we ignore. That's basically the moral of the story. And so if we want to know how much time does it take to do, say, 1,000 versus the amount of time that it takes to do 100 elements in whatever algorithm it is, we do c times 1,000 squared divided by c times 100 squared. And the cool thing is you see that this extra constant that I've added on will cancel out, right? So the constant cancels out. And so what we're left with here is 1,000 squared divided by 100 squared, which is equal to 1,000,000 divided by 10,000, which is equal to 100. So you notice that the amount of time, really the ratio of time, right? We're taking the time that it takes to do 1,000 things divided by the time that it takes to do 100 things. And it doesn't matter if you make this 1,000,000 divided by 100,000 or 1,000,000,000 divided by 100,000,000 or whatever, it's still going to take the same amount of time. Oh, the 8s, I didn't even notice. So you notice that the ratio of time for an n squared algorithm is the ratio of input sizes squared. Wow. So that's a pretty cool little fact, and we'll talk more about that next time. I didn't really do any multiple choice examples. I'm going to go through the multiple choice and make sure that there's nothing too crazy on it. But I'm probably just going to give you guys the multiple choice sometime today, and you'll have until next Monday to submit it. So that's the answer with the multiple choice. And so next time, as I say, we'll discuss algorithmic complexity, and I'll tell you what, we're going to do some binary search stuff next time, and we'll talk about the algorithmic complexity of that. So I know this is searching and sorting. I really only did sorting. But the cool thing is that we have 5 algorithms. We have bubble, insertion, selection, merge, and quick. Right? Those are our 5 sorts. And if your question is, are there other sorts? The answer is, of course there are. The first additional sort you might have is something called heap sort. Heap sort is also a logarithmic sort, but it's a little more advanced. As I said, you need to basically you take 341, you learn about heaps, and then you turn that into a sorting algorithm. So that's what you generally do. There are other sorts. One of our TAs really loves something called BOGO sort, which is basically the worst sort. It could possibly be, I'll check. It's the worst sort that actually does something at every step. So every step is not wasteful, but it does something at every step, but it's also basically the slowest sort possible, given that restriction. So if you make it so that the complexity of BOGO sort is actually O of n plus 1 factorial, and we will talk about that next time. So what BOGO sort does, and of course I'm like 5 minutes over, but I'll let you go after this. So what BOGO sort does is it just randomly shuffles, and then it asks, sorted? If not, generate the next shuffle, keep going. This particular TA is always amused by the kind of bad performing things in the universe. I mean, TAs, once you take 341, you start to like, everything has runtime O of n squared, O of n log n, maybe something has O of n cubed runtime. But how often do you see something with a runtime of O of n plus 1 factorial? Not often. So it's just, they don't like it as an application of a sort. They like it as a cool little example of, like the worst case of things. So anyway, maybe we'll talk a little bit about BOGO sort. We'll talk a little bit about binary search. We'll talk about how to kind of think about the algorithmic complexity of quicksort and merge sort. And I've taken up way too much time, so I'm going to let everybody go. So is n plus 1 factorial better than n squared? No. So remember, when it comes to time, lesser is better, right? And so n squared is way, 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 way smaller than n factorial, or n plus 1 factorial, or 2 to the n, or whatever. So whatever takes less time, right? Whatever takes less time is better for us, because for us, our idea of calculating is if we have to wait 2 years for a calculation versus if we have to wait a week versus if we have to wait 10 seconds. Generally, we want to wait 10 seconds. Maybe you have some Zen reason that you want to wait 2 years, but in principle, as computer scientists, our goal is to get a calculation done as quickly and efficiently as possible. And so n squared is way better, right? So what are the lesser times are better, and n plus 1 factorial, it dominates n squared in a way that is hard to even really describe. Like both of them go to infinity, but when you do n plus 1 factorial, it makes n squared look like it goes, like if you take n squared divided by n plus 1 factorial, and then you take, say, the limit as n goes to infinity of this thing, it's going to go to 0 pretty quick. So basically, n plus 1 factorial absolutely smashes n squared. It dominates. And we'll talk about that more next time. Basically, the next 2 lectures are going to mostly be math. I'm going to try to make them a little bit more programming-centric. Generally, people hate all the big O complexity stuff, and I understand. So we used to test it really hard, and everybody failed that portion of the test. So I decided not to do that anymore, because I learn. So anyway, I'm going to let everybody go now. It's only 10 minutes after, so oops. The good news is that all the extra stuff really is unnecessary, so... Yeah, I mean, I did teach calculus for, 10 years, so... I vaguely understand calculus. Alright. Have a good day, everyone. That's it. Wait for the MCQ. Do the test. Start working on the project, etc., etc. Bye.